All right, line A1, learning test 6, we're going to take a look at problems with AC values. In particular, we're going to go through solving a bunch of problems. Before we even begin this video, I need you to pause, go back to your Blackboard shell, and I need you to go and open up the document that is going to be labeled ITA formula sheet. This formula sheet is going to be your only formula sheet that you are going to be allowed through the entirety of second year. And the reason for this is not because I want to cripple your learning or anything like that, but because I want you to get used to the formulas that are on here, because when you finish second year, you're supposed to go and write a standard level exam from the ITA, and this will be the only formula sheet that you are going to have. Same with when you finish third year, you will go and write a standard level exam, and you once again will have only one of these sheets. And when you write your interprovincial, you are also going to go and have a formula sheet that is provided for you. So I want you to be able to find the formulas that you need on this sheet, and I want you to memorize the formulas that are not on this sheet. There's going to be some that are not going to be on the sheet, and so I'm going to identify those with you as we go through these modules. You're going to memorize those, and that way, when you actually hit these exams, you're not going to be sitting there scratching your head and wondering, oh, what was that, exam that I need? So I'm just going to pause right now and go and open that up. All right. Now, with that one running in the background, we're going to go over a bunch of sections on it. I do want to just highlight really quickly that it's broken down into a couple of general sections on here. We've got one section that is going to be just my general sections, just a heading up top here for general. We'll use that anytime that we are looking for most formulas. I've got another section on the other side that is going to be electronics. We're going to see some formulas that look similar to what we need right now, but they're not going to be quite the same. We're going to talk about that in a minute. But these are going to be strictly to deal with electronics and with rectification and power and things like that that are going to be inside of it. The last section is going to be dealing with rotational machines, so motors and alternators and things like that that are spinning around. We are going to go and take a little bit from there because right now we're going to start by taking a look at the generation of AC values of voltage, which means that we're going to have to take a look at some machine formulas. So for now, we are going to be working in the general section, as well as we're going to be working in the machine section. We do not want to be trying to take and apply anything from the electronics section yet. We'll learn about those, and we'll figure out how to properly apply those later on this year. But at this point, we want to kind of ignore that section. Let's start by taking a look inside of our machine section. Right near the very bottom of our machine section, you should see a set of boxes that are going to go and look like this. And the formula sheet doesn't tell you what each of these each of these letters are going to go and represent. It just gives you the letters, and you're supposed to go and remember what's going on with these. These are going to be my frequency and poles formulas that I'm going to go and have. F stands for frequency. It's going to be measured in hertz that I'm going to have. So I can figure out hertz if I know either the number of poles or if I know the number of pole pairs. Note that if I have the number of poles, that would be a north and a south on a machine. Whoop, north and a south on a machine. Come on. North and a south. Oh, I don't know what's going on here. Things are going crazy. There we are. If I've got a north and a south, that would be two poles. So if I wanted to count each pole, I'm going to go and use this formula. If I wanted to count them together as a group, as a pair of poles, I would use this formula. And note that this one over here just is not divided by 2. This top one is divided by 2 because it's got, two pole pairs. I don't care how you want to go and look at it. You pick one that you're going to go and work with, either the number of poles or the number of pair poles. I'm going to go and work with the number of pair poles throughout the bulk of my formulas later on inside of third year, because that's what most of the third year is going to cover, and that's where you're going to be heavy into your rotational machines. However, inside of this module, they do work off of this one, where it's 2 times 60, but you'll note that in your book it says 120. Once again, potato, it's the same way of writing the same formula. What I've got as well, I've got frequency that's identified inside there. I'm also going to go and have N. N is oftentimes going to be referring to rotational speed of a machine. We'll see it in a bunch of other formulas that are inside of this section over here where they're going to have N values as well. So we'll deal with that one as being RPM. Why is it N? I have no idea. Absolutely none whatsoever. But it's always been N for probably since the 1800s or something like that. Somebody had some reason for it. It became N, and it has just stayed as N. So just recognize N in these formulas as standing for your RPM. Okay, let's go and take a look at the actual problems that they're asking us to go and solve. So the first problem that they're going to go and say is, what's my frequency if I'm going to go and have an 8-pole alternator that is turning at a speed of 750 RPM. So obviously I'm going to be looking for frequency. I could use either one of these. I can take the top one over here. N is going to be my RPM. So that would be 750 RPM that I would put in for there. P is going to be my total number of poles. They said it's an 8-pole. So I'd go 750 times 8 divided by 2 times 60, which is 120. And that's going to go and spit out a value of 50 hertz. Note that if you do this bottom formula over here, and if I do the same 750 RPMs, but now I go with 4 pole pairs, a pole pair being a north and a south, if you go and punch 4 times 750 divided by 60, you're going to come out to the exact same 50 hertz. We start by looking for frequency. Frequency is the number of times that a waveform repeats itself within a second. I have no clue what's going on here today. Oh, 1 second, actually. I do have a clue. Go back to that one over there. Frequency is going to be the number of times within a second that a waveform goes and repeats itself. So from where it begins, right over here, to where it begins to repeat itself for the next waveform, to the next waveform, to the next waveform. So the number of waveforms we have per second. You should remember that from your first year materials. The second one that they take a look at is they ask, what RPM. So they're going to go and take the same formula. They're going to go and move it around. They're going to go and develop one of these 2 formulas. They're going to be asking for speed. The speed is going to be based upon 2 times 60 multiplied by my frequency divided by either the number of poles that I have or the number of pole pairs that I have. One or the other. Once again, just parachute your numbers into this thing based upon what we are looking at. So we know that we have got a frequency of 60 that we are looking for. And we know that we have got 10 poles. So we would go and put that 10 inside of there. No clue what's going on. I thought I knew what was going on, but apparently I don't. And we have 10 over here for this one. So sorry about that. I think I got it figured out. I think it was just a low battery on my mouse here. Kept jumping in and out, thinking I was mouse clicking. All right, back to where we just were over here. Number of poles is going to be 10 poles. We could also do the same formula down here by asking for 60 hertz up top here and going with 5 pole pairs. Either way that we go and put these together, we're going to go and spit out the same value of 720 RPM. Grab your calculator, put these in. Make sure if you're doing this 2 times 60, if you're doing anything that you're dividing or multiplying by, that you're bracketing that, or just put that in as 120. Either one of those is going to go and work. The very last problem that they go and talk about is the alternators at Ruskin Dam, which is just outside of Mission, for those of you that don't know it. They turn at a speed of 120 RPM, produce an alternating voltage at 60 hertz. And so how many poles do these alternators go and contain? This one we don't have a formula for, so you are going to have to go and extract the P out of one of these formulas. The easiest one to go and pull that P out of is probably just to go and cross multiply the N and the P out of these ones here. Pull that up to the top over here so that you're going to go and have P is equal to my, we'll call that 120F divided by N that I'm going to go and have here. Once again, drop in your values. Frequency of 60. Speed of 120 RPM. They're really low speed, by the way, most of our alternators inside of hydroelectric dams. And then once you go and multiply all this together, you're going to find out that basically this top 120 and the bottom 120 will cancel each other out, and we end up at a value of 60 poles. These are really large, flat, cylindrical alternators that travel at a relatively low speed. You'll learn lots about them later on once you get into third year. Okay, the next thing that we're going to go and take a look at is conversion factors for resistive AC circuits. We're going to see a lot of tables that are going to look very similar throughout this whole set of modules. And a lot of times they're going to be identified as being either for resistive or for inductive or for capacitive. And we have to be careful that we're utilizing the correct ones for that. Right above this table here at the very top of that page there, it does talk about, back in Learning Task 2, which is an error that you would have been introduced. Don't worry so much about that. What we do want to look at on this table is we want to see a bunch of values that are given to us, and we want to identify the ones that are not given to us. The ones that we do have is we should go and have this one over here, my maximum value of voltage. That is going to be based off of my BLV out of my table there. Oop, I don't have that one over here. Let me just go and erase this. We will grab this over here. On your ITA formula sheet, you should find this formula over here. We are also going to go and take a look at this one over here, which is going to be my instantaneous value of voltage. So identify those on your sheet. We're going to now refer to them back here inside of the module. Inside the module, we talk about this EM, which is going to be my maximum value of voltage. The maximum value of voltage is going to be based upon whatever I have got for flux density, length, and velocity, and we'll cover all of that later on. And it's going to have values that are going to be split between alternations, which is just going to be half of a frequency cycle, and full cycles, which are going to be over top of the entire frequency cycle. The next value that we are going to go and have is going to be an E without a subscript. Now, E and V are used interchangeably in a lot of cases. There is a technical difference between them. E is technically for anything that is generated, value of voltage. So a source will have its volts measured in E, technically speaking, and a load will have its voltage drop measured in V that we are going to go and have. We do see a lot of mixing across there. I'm not going to fault you on that as long as you don't fault me on that. I'm going to try to use E's whenever we're looking at sources. I'll try to use V's whenever we are looking at loads, but this is just something that gets, pushed back and forth. So if you really want to be correct in your electrical terminology, use E's on all of your sources, use V's to go and designate any sort of a voltage drop you have on a load. Anytime that we see an E or a V or a voltage value that does not have a subscript, it means that this is going to go and be my RMS value, which stands for root mean square. We also call this our effective value that we would go and have. And it's a complicated method that they go and use to go and develop this whole root mean square, but it works out to become 0.707 of whatever my E max is going to go and become. And this is going to give me the same sort of effective heating as if I had a DC supply. We'll take a look at that one later on. If you don't subscript, if you are asked for an answer inside of a question, and if you do not identify it with a subscript, I take it as being an RMS value. This is going to go and lead to lost marks for some of you who aren't listening or aren't going to go and pay attention later on. If I'm asking for an average value of voltage, make sure that you identify it as E average. If I'm asking for a maximum, identify it as EMM for that. If it's just an RMS value, or if I don't say what the value of voltage is, then we're referring to our RMS values that we're going to have. RMS value is not going to go and be shown on your ITA sheet. They don't have that anywhere up top over here. They don't have that anywhere down here inside of the bottom. It is just an assumption that you would have that memorized before you ever end up at a standard level exam or interprovincial. And the way that we find our effective or RMS value is we go 0.707 of our maximum value. If we know the peak voltage, we'd multiply it by 0.707. Same with the next one down over here, which is going to be my E average. E average is different than my RMS. RMS is just the amount of effective value or force that we're going to get out of it. Voltage is a type of force. Average would be a true, pure mathematical averaging of my sine wave. You'll note that the true, pure averaging ends up at a slightly lower percentage over here, 0.637, compared to this 0.707 that I'm going to go and have for my effective value. Know those two differences. Once again, there is also a place on your formula sheet where you can get screwed up on that. Remember that we are not using this section yet, the electronics. There is averages that they're going to go and ask. In fact, there's even one average that even contains the number 0.637 inside there, but it's also got a root 2 off of it. These are going to be averages that we would use later on when we are trying to go and develop half wave and full wave rectified types of circuits. So for now, do not use these as being average. These only work inside of our electronic circuits. This just means that these two are going to have to be memorized values for you. 0.637 is going to be your average. 0.707 is going to go and become your Emax. The next one down is going to be my instantaneous. I'm able to go and find the instantaneous value of absolutely any value of voltage by going and taking the sine of whatever angle it is multiplied by my maximum value of voltage. In other words, if I take a look at a full sine wave, that full sine wave takes place across 360 degrees. Because it takes place across that full 360 degrees, I know that halfway through here is going to be 180 degrees. I know that this peak and this peak are each going to be at, this is 270. This one over here is going to be at 90 degrees. And I can find any value of voltage anywhere along there. We will use this one when we get into some of our thyristors inside of third year. It's an important formula that you're going to have to hold on to, remembering that that sine theta multiplied by your maximum is going to give you an instantaneous. After the voltages, we then get into this section over here, which is going to be current. Current is going to go and have the same types of layouts. First of all, we're going to go and see capitals, which are going to be standardized values. Maximum current happens when I get maximum voltage divided by my value of resistance. Resistance doesn't have a RMS or an average or anything like that, because resistance is all based off of R is equal to K times L over top of CMA. It's based off of physical constants that we are going to go and have. They lay those out for you on this formula sheet over here. K times L over top of CMA, and they even give you the mil foots, the amount of ohms per mil foot that you are going to go and have for copper and for aluminum that are going to be on there. Because resistance stays as a constant, K times L over CMA, based upon the physical properties of that material, we can then go and take our maximum value of voltage over top of that fixed value of resistance. That's going to then tell us our maximum value of current. If I've got a maximum value of current, I can go and multiply it by 0.707 to go and get my RMS value, or my effective value of current. And if I've got a maximum value of current, I can take my 0.637 to get my average value of current. I want to point out as well that this is not the only way to go and get your RMS value of current. The other way you can get your RMS value of current is just to go and use your E RMS divided by R, right? We got a non-subscripted E over here, which means that we're dealing with an RMS value. We could just go and use RMS values with the resistance, get RMS current. That is going to go and happen back out. Same as we could go and use E average over top of R to go and get my I average current out. Lowercase I is going to go and identify it as an instantaneous. Instantaneous is once again coming with sine of the angle off of my maximum value of current. Power maximums. Power maximums are going to be found when I have my maximum voltage multiplied by my maximum current. I'm going to have my power maximum. And for the rest, my effective amount of power is going to be half of my maximum power, also known as just my RMS volts multiplied by my RMS amps over here. Note how neither of those is going to be subscripted at that point. The reason for that is really if you go and take 0.707 times 0.707, you end up at 0.5, and 0.5 times your power max. It works out, mathematically if you go back through it, but we're not here for mathematical proofs. We're here for electrical concepts. So work with this formula most of the time. My true power, measured in watts, is going to be my volts times my amps, all in RMS types. Average power is going to be the same as my RMS type of power, which leads to a really, really interesting thing. Because if my average power and my true power are equal to the exact same thing, what is the point of my average voltage and my RMS value voltage? Well, the point of my E average is my DC equivalent, is what it is. Basically, this would be if I'm going to go and take this thing down into a DC type, then I would be able to go and get the same amount of power out, right? Power is the total amount of work that is going to be done by a circuit. So we want to know that no matter what values we are using to measure the volts and current, that we at least know the total amount of power and it's the same across all of our circuits. Let's do some calculations off of these ones. Just erase a bunch of this. Examples 4, 5, and 6 are all dealing with average or RMS values. The first one that they ask is, what's the effective value of a sine wave with a peak voltage of 491 volts? Well, if it's a peak value, I know that I can then take a maximum and multiply it by my 0.707, which is going to go and get me down to my RMS value. You would be using this formula, 0.707 multiplied by your E max over there. 491 times 0.707 gets you to 347. If you go and do 170 times 0.707, you're going to get to 120. That's what we refer to as 120 volts. It's actually got a peak of 170 volts. The next example talks about what's the peak value of a sine wave that's got an effective or a RMS value of 277 volts. Well, if it's a 277 volts, what I can do is I can just work this formula in the opposite direction, right? If RMS is equal to 0.707 times my E max, I'm just going to go and divide 0.707 out of both sides, which is then going to go and leave me with, take my RMS value divided by 0.707, and it's going to kick me over to my peak. This is going to become a formula you're going to get very familiar with as well this year. Take any RMS value, divide it by 0.707, and you're instantly going to be at the peak value of that voltage. Try it with 120 volts as well. Take 120 divided by 0.707. You should go and equal that 169 points, I think it's 0.86 or something like that, but we roughly say it's about 170 volts. Example 6 is a little bit harder to grasp. It talks about what's an average value of a sine wave current with a peak value of 35 amps. Well, when they're talking about average, they're looking at this thing from a DC perspective. And if it goes into the positive range, and then it also goes into the negative range, and it goes an equal distance into both of them, obviously the average value is going to go and be 0. We can only use the DC average values over top of a single alternation. This doesn't make much sense right now on the whole averaging, that we can only use it over top of a single alternation, because we haven't dealt with rectification yet. Once we deal with rectification in electronics, it will make more sense, because in rectification and electronics, what we do is we go and we only pass a single alternation at a time. We can never pass a full cycle at a time. We can only pass alternations from it. So we will see these ones later on. Don't stress too much about these ones. It's example 6 is a little bit of a tricky question. They're just saying, look, you can't average, you can't take a DC average over top of 2 of these, both up and down. Example number 7, what is the average value of one alternation in example 6? That we can do. So that one, you could take that 0.637, multiply it by your maximum current, which was 35 amps, and that will then give you an average across a single one. The next couple of examples that they're going to give you are all to do with power that we are going to go and have. What is the peak power in an AC lighting circuit? That is 1200 watts. Well, we're going to find out that our peak is going to be double for that. Of what our effective power is. So we can go and use that formula. P is equal to the 0.5 times my maximum power over here. When you go and punch that in there, you're going to find out that you're going to be at 600 watts. We actually have double the amount of power at the very peak, but then we also have those dips where we're not seeing a lot of power in between there. Example number 9 asks you for an instantaneous value, and instantaneous values are going to be found off of this formula over here. Take your maximum value of voltage, take a sine of the angle, in this case sine 30, and then that is going to go and get you your value. Now they do give you an effective value of voltage, which means that for example number 9, what you actually need to do is you need to transfer from your RMS up to your peak value, and then from your peak value you're going to have to go and find that instantaneous value. Last of all, for example number 10, if the instantaneous value of current 60 degrees into an AC cycle is 173, what is the effective value of the current? Well, this one you're just going to have to work backwards out of your instantaneous one. Out of that one, you're going to work backwards from that one until you can go and develop your maximum amount of current. Once you've got your maximum amount of current, you can then take your maximum amount of current and you can multiply it by 0.707 to go and get your effective value of current. I'm not stepping through each of the calculations. We're just explaining what the formulas are for those. You've got lots of study time yourself that you're going to have to go and make sure that you're on top of. So go through those formulas, go through the self-test as well for these ones. Let's take a look at the next set that we have inside of here. The next set of pictures that they show us over here is just an explanation of what we have got for RMS values compared to DC flatline value. A DC flatline voltage, so in other words, a source that puts out steady voltage, 1 volt DC over here, over top of 10 ohms, is going to go and give me the exact same amount of power as a RMS. This is a 1 volt AC RMS. Note there was no subscript off of it, over top of the same value. This is why we call it the effective one, because this allows us now to use the same formulas across all sorts of different calculations. We're not bound by, that we have to go and use this one only now, and then we have to change our whole calculations when we're going from AC to DC. That whole fact that we're just using these effective or RMS values means that we can just utilize, our calculations properly. We don't have to do a lot of extra work out there. What does this actually look like when we run this through the sine wave? Completely through the sine wave, we end up seeing something that's going to be a comparison like this. This is the exact same two circuits that we're going to go and have. The first one over here is showing that, look, we've got a 1 volt. We're going to go and have a small amount of current, and if I go E times I, it's going to go and give me a peak value of DC, and it's going to be a constant value of DC. If I compare that over to the other sides, where I've got a bunch of waveforms, what I'm seeing is that I've got a sine wave over here that is going to be my voltage. We know that when I hit my maximum value of voltage, I'm also going to go and hit my maximum value of current, right? We've got that right over here. When I hit my maximum value of voltage, I get my maximum value of current. So we see that off of this one here, that we have maximum current peaking at the same time. And we also know that my power is simply going to be a multiplication of my volts times my amps. If I multiply these amps and these volts together, I come out to this total amount of power that is going to be up like this. You multiply them together down here, they start building power, you multiply them together, we hit this peak. It peaks with these two at the same time, then it drops back down to here. And then over here, we now go to a negative current and a negative value of voltage. Once again, if you go back to, simple base math, a negative times a negative is equal to a positive. So if we have got this over here, it's just simply because we're taking a negative times a negative. You got to think, what is power itself? Power is watts. It is heat that is going to go and be given off by something. I don't know if you've got a ballpoint pen in front of you, but a ballpoint pen is probably one of the easiest ways to understand that this is going to go and generate heat no matter which direction our volts and our currents are going to go in. There used to be this thing, I don't know if people still do this, but back in high school, I remember that if you had a really cheap big pen, what you do is you go scribble back and forth, back and forth, back and forth, back and forth, and it makes that noise. Everybody knows what it sounds like when somebody scribbles a ballpoint pen. And if you scribble it back and forth, the tip of that ballpoint pen gets hot, super hot. And so what you would do, or maybe not you, but people would do, is they would scribble it back and forth, back and forth, back and forth, and then they pick it up and they go tss, and they touch it to the back of the neck of the person that's sitting in front of them. And, it gives you a little burn, and the person in front jumps, etc. It's hilarious, the class laughs, etc. What we have is we have heat. Where did that heat come from off the ballpoint pen? It came from the fact that we had a mechanical component, that little tiny ball that's inside there, that is being pushed in one direction, and then is rapidly being pushed in another direction, and then is rapidly being pushed in another direction. Back and forth, back and forth, back and forth. And that's where we generate that heat. That's what happens inside of an AC circuit, is that we are going to have electrons that are going to be driven through the circuit in one direction. And then we're going to go and drive them back in the opposite direction. And then we are going to go and drive them back in the opposite direction. And we are going to generate heat because of all those little collisions that are going to be happening inside of there. When I take my ballpoint pen and I go forward, it's not like I generate heat and then I generate, refrigeration or coldness on the backstroke, and then heat and then coldness and stuff like that, and that it cancels each other out. No, we don't see that. What we see is we see heat, 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 back and forth as we go across there. The same thing happens inside of our AC circuits. We're going to be generating heat continuously just by the fact that we're moving electrons, and then we're switching around. We're pulling them down the opposite direction, but they're still colliding all the way through. It's an interesting looking graph. What I do want to point out about this graph is that we see the peak, and we're dealing with only pure ohmic resistance right now. I see the peak of this one that is lining up with the peak of my current and the peak of my voltage simultaneously. All right. Let's just erase a bunch of this over here. All of that is scribbles. I don't know, maybe high schools have changed a lot since I went to high school. Sometimes when I tell this story, classes look at me, back in the old days when we had real live person classes would look at me and be like, I've never heard of that before, but maybe their school was just a kinder school than the one that I went to. Who knows? All right, let's go take a look at examples number 11, 12, and 13. 11, 12, and 13 talk about, once again, where we're going to have peaks and where we are going to go and have RMSs. If you take a look at example number 11, 11 is asking us to go and deal with a voltage source that's a peak over top of a resistance, and then what sort of power is it going to go and dissipate. And so this one is starting to bring back in a bunch of your Ohm's law. You should be familiar with Ohm's law and with your Watt's law. They're not given inside of here because it's just assumed that you've got those memorized, right? Watt's law, watts is equal to my E times I. We also know that watts are equal to my I squared R, as well as watts are equal to my E squared divided by R. All of those formulas are going to come into play. We're going to use this formula actually a fair bit, the voltage squared over top of the resistance, which is going to give the power, because most of our electrical circuits are going to be connected in parallel, which means that all of our values are always going to see the same value of voltage over top of them. And so it makes it a really handy one for us to use. So expect to see that one a fair bit, get familiar with that one. And for the rest, it's just going to be straight Ohm's law that we're doing through a lot of the rest of these as well. I, E, and R that are going to be associated together. Let's talk about, maybe I should write that one out there. Should be familiar with the triangle like that, where you can go and select any one of those to go and find values off of them. So the first one shows us if we got a peak value voltage and a resistance, what sort of power. What you're going to have to do on that first one is you're going to have to go from your peak value voltage. You're going to want to go to an average value voltage. Once you've got an average value voltage, you're then going to go and use your average value voltage with that formula to go and develop, and with the resistance that's given, to go and develop your watts that you are going to go and have. If you wanted to know what the peak was going to be, and that's what your next question is going to be, what's the peak power of the circuit in example number 11, all you're going to have to do then is go and take this formula right over here, you know, that my effective amount of power, which is what we developed over there, is equal to half of my maximum power. I'm going to take this, put that in as that value, and then work that formula through backwards to find that my peak is going to go and be double that value. Next question that they have, example number 13, what value of peak current is going to go and have to flow through a 60 watt 120 volt lamp to cause it to dissipate 60 watts? Well, what we're going to have to do is we are going to have to go and figure out my RMS current, and then from my RMS current, then we are going to go and figure out my peak, because all these ratings that are given are without subscript, 60 watt 120 volt, which means that they are RMS values. So I'm going to go and take this formula, power is equal to E times I. I'm going to isolate for I, and that's what they show them doing. Once I've got that I, I'm then going to go and take that I, and I'm going to go and work with this formula, and I'm going to take that I, put it into here, and then work this formula backwards to get my maximum amount out of current, which is going to go and work out to be a higher value than my RMS one. Example 14 talks about effective AC voltages. So what RMS value voltage must be applied across a 1200 watt load to get the rated peak current of 7.07 amps to go and flow through that load? Well, what I'm going to have to do is figure out what I'm going to go and have for a effective value of current first. So I'm going to go and start with my, I'll take this one down over here. Start with this one over here. And if we're looking for a peak, I'm going to go and put the peak in over here, multiplied by 0.707. That's going to go and tell me what my RMS value is. Once I've got that RMS value, I can then work it backwards through this one over here. Stick that RMS value into there, work this formula backwards based upon that 1200 watts and that current, and it's going to go and tell me the RMS value of volts. Last example, working with the same sets of formulas that they have over here. If a voltage with a peak value of 491 is applied across a heater to produce heat at the rate of 1500 watts, what is the heater's resistance? This one is a little bit more tricky to go and sort out. But basically, what we're going to do is we're going to go and take that peak value of voltage, we're going to go and transfer that thing into an RMS value of voltage. That RMS value of voltage, we are then going to go and put that RMS value of voltage into here along with the heat that we have, the 1500 watts, and then we're just going to go and cross multiply the R and the W isolate, get the R up top, bring the W down below, which is then going to allow us to figure out the amount of resistance that we're going to have. This example number 15, make sure that you can nail stuff like that. It's a common one where we're going to go and see changes in values of voltage. We're going to have watts, stuff that's going to be rated to go and put out a certain amount of power, but then we are going to change the value of voltage, and it's going to change the watts or the output characteristics of it. So we'll use this one throughout second, third, and fourth year to go and explain, voltage drops and sags and things like that later on. Just get familiar with it. Go through your self-tests. Make sure that you're getting all of those values. If you're not getting those values, go back through until you find out where you've gone wrong. Be very careful. Always identify whether you're looking at an average, RMS, effective, peak, whatever that is going to go and be, and that you're using the correct formula for that.